Now it's in this course, as we have written over here, we have three parts. The course is divided into three units. The first unit is introduction to VLSI testing, and then in second unit is about test methods, and then design for testability. So in this lecture, we will see what are the content of these three units and what will be the outcome after concluding all these three units of the course. And especially we will elaborate this first unit, introduction to VLSI testing, in today's session. So first, while introducing this course, I would like to remind you the VLSI realization process. So in VLSI realization process, we start from customer's need, and then we finalize it to a product, and then we deliver that product to the real customer. So in between this flow, first a team will be so in this process, we first define the design requirements, and we write the specifications in registered transfer logic in RTL format using hardware description language. I hope the students will be aware of hardware description language. This is a system which will be used for defining hardwares, the real hardwares, in the form of FSM. Okay, so after writing this specification using some EDA tools, electronic design automation tools, we synthesize the design and verify the various implementations of the design, and then we do the test development process. And after gathering a confidence matrix or test coverage, that how much is our design correct, that we will evaluate using multiple verification process. And after evaluating these verification methods, we will go for fabrication. And finally, we test manufacturing devices through manufacturing testing. Then we deliver these things to customers. So the time taking from the beginning to end is known as time to market. So the companies are using efficient verification process. Companies are reducing this turnaround time, like how much time they are spending in test development after gathering the evaluation of verification process. How much time they are changing the specification. It is related to verification turnaround, like how much complex it is to do the verification of in all aspects. So this is all about the verification process and test development process. So there are certain types of fault models, and certain basically a fault is where a device stops working at a point. So this will be known as fault. So we have different fault models depending upon the different levels of design. Like we can see a design. We can see a design in different levels. Like we can see a device on transistor level. We can see the device on gate level. Okay, so these are the various implementations which we can see, and we can define different fault models depending on this level of abstractions of design. Okay, depending on this selection of a fault model, there are variable test development methodologies. Okay, so we will see in the detailed course all these things. So now this is first, you can see the technology direction from 1999 to 2014. Here we have observed that feature size is decreasing, and how many million transistors can be formed on per centimeter square area is increasing. So these are the things how technology is extending the Moore's law in recent years. Okay, so basically on these parameters, on the study of these parameters, we can say in recent time the complexity of these hardwares or RTL designs, or the implementation of verification on those design is getting increases year by year. The complexity is getting increasing. So basically, why it is important to do the test and how we will do the test And basically, what will be the fraction of the cost, total cost, will depend on the testing. It is the important part of this VLSI realization cycle. So basically, uh, sir, hello, am I audible now? Hello, sir. Students, so I can also just also interact with the students. In initially, we have only 4 to 5 people, so that's why I was not interacting all of them. Okay, so is there any query you can ask in the middle? Okay, so we will elaborate every terminology to you. Okay,
Okay,
so
sir.
I'm presenting the again, and if you want to go back to any slides, you can interrupt me in between. Okay. So basically, if I summarize whatever I told, that it is there is some VLSI realization process which turns some design specifications into some product, some integrated circuit, and deliver that integrated circuit to the customers after testing that whole device. So generally, the device gets fabricated in batches, and the companies will do the mass production of this design. Okay, so if we will do the mass production, so basically we have to do the manufacturing testing, like the physical device, how it is working, how it is working. To check those devices, we use ATE machines, automatic test equipments. Okay, so here I am mentioning this new term ATE, automatic test equipment. So basically, after getting some design or some chip physically, there may be some fault because of defects. Okay, so in fabrication process there are some standard process that gets used, but still there can be some defects, and based on and these defects can be models by various faults, and then by analyzing those faults we will pass or fail any implemented physically implemented device. Okay, are you getting my point now? So basically, test time. The AT takes a huge amount of test time to perform a test application for a specific design. And basically, if after testing a number of integrated circuit, if we found that some percentage of the whole batch was not good product, so we can here define the yield loss and how much the company is investing to develop a design and how much good design they are producing, and what will be the flaws, what are the flaws which are making these designs degraded. So to evaluate these things, we do the test development process. So basically, in manufacturing, in test development phase, the test development phase I have shown here, what we will do, we will just simulate the device like we testing on ATE machine, physical in physical form. Okay, सो जैसे हम फिजिकल फॉर्म में उसको टेस्ट करेंगे, मैन्युफैक्चर डिवाइस को, आईसी को, उसी को सिमुलेट करेंगे टेस्ट डेवलपमेंट में, उसी को सिमुलेट करेंगे टेस्ट डेवलपमेंट में, एंड देन वी विल सी व्हाट विल बी द ड्रॉबैक ऑफ द future test we are going to perform on manufactured device, and then we will optimize the process and optimize the design itself, and then we again do the test development to gather the evaluation of verifications algorithms we have applied and testing strategies we have applied. Then we do the manufacturing test after getting a good amount of confidence of the design or good amount of result of test development. Okay, so basically, test development process takes 80% of the cost of the design. Like there is a IC, XXXX is the IC, and you are going to purchase this 1800 rupees. So 80 to 70 to 80 rupees of the cost will be related to the testing cost, test development and manufacturing test. Only 20 to 30 rupees will be the cost that will be used to manufacture that IC. Okay, so it is important to test. So basically, compression is here. So to test any device or any chip, like you have a design of full adder, which you are going to test. So what we will do, you can just to verify the functionality, you can write a truth table, and you can verify that truth table that for all the inputs, it is giving the good output or not. It is giving the output that is defined by the truth table or not. So this is all related to functional testing. And now we can see that how we are applying the patterns, input patterns, to test the circuitry. So basically AT have limited memory space and limited bandwidth to send the patterns to the IC we have embedded on this AT machine. So basically we use test data compression here. Basically we compress the pattern so that it could use low memory to save the cost of testing. And we also do the at speed testing, like to process, we implement something so that we can do the we can perform faster cycles. Basically we can perform faster test cycles. Okay, then we can define some new fault models for concerning any specific defects, and we can uh, apply some different strategies to those faults, basically. And also the power delivery issue is there, like if we testing some chips and it is dissipating uh, a huge amount of power while testing, so we can also have some yield loss because of power issue. Okay, so these type of issue is in concern with testing and verifications of VLSI circuit. So is there any doubt till here? Should I repeat something? So, or you guys know something about VLSI testing and verification? It's not audible. Please give me somebody give me any answer. Okay, I'm just going next slide. So basically, there is separate design house and there is separate fabrication house for processing a single chip. So a design will be simulated and tested in design house, and then some implementations. Like I think you might have studies about RTL to GDS2 flow, which is also basically in this VLSI realization flow. After determining requirement and writing specifications, we do design synthesis verification. And along with this design synthesis verification process, we also generate multiple implementations of a design. And one of its implementation is GDS2 file. And this GDS2 file will be delivered to the fabrication house or fabrication vendor, and then they will fabricate the same design, whatever the specialties or whatever the specifications are there in GTS2 file.
Sir,
Yes,
sir, what the different methodologies that we used during testing in test generation? The same
test
methodologies are used for DFT also after manufacturing.
basically test generation is about the is related to fault modeling. Okay, and DFT is related to, you have an idea of fault model, and you know what could be the fault site depending upon the fault model. Okay, and then you can apply the different structures so that you can perform some simulations by producing the input. So in DFT have some different methodologies, and test generation have some different methodologies. Okay, but basically both are depends on each other. Like if you want to do test a combinational circuit only. Okay, so you can do this combinational testing using D algorithm, and D algorithm is related to ATPG, automatic test pattern generation. Basically, it is related to test generation, and But in DFT side, you do not need to apply any scan-based testing or beast to just test those combination circuit, because that these combination circuits are not that much complex. But if you will see, if you want to test any sequential circuit or a real-time hardware that have some memory elements, like they have some flip-flops, then you have to apply some strategy to just to initialize the memory content, flip-flop content, so that the memory can be turned into a known state, and it can be used to check what output it is giving on some set of inputs, and what are the change in the state of the memory, okay, to test these things, and what in what state we make, in what state we want to make transition. That will be defined by test generation. Okay. Are you getting some? I have given your answer of your question now.
Yes, right.
ATP, the algorithm, PODEM algorithm, these are the part for test generation, and they have different algorithms. And DFT is the part where we have just categorized the designs, and we have some different methodologies for those designs. And there are a relation that for these types of DFT we will use this type of algorithms. Okay.
Right, sir. Yes, sir.
So in next session, in next part of the unit second and unit third, next part of the course, you will see these things in the detail. If you follow the book, electronic testing book, Bushnell and Agrawal book. Okay. So basically, this is about a conversation between a design house and fabrication house. Basically, they have a contract, and they give them the GDS2 file and other information of design, and told them to basically fabricate this design with this technology. And while they fabricate the design, they ask that you have gathered enough confidence metrics now, you have tested the design now. If have some, because every vendor will have some certain amount of defect, so it will just told them there will be some tolerance that maybe 1% defect may be there. So you have tested your design now, so that it can be the cost could be optimized. So this is the thing. And there is also what type of DFT strategy you have used, and what type of test generation you have used, and what fault models your test generation is covering. So these questions will be documented to design house or through vendors, and after seeing this history, the vendor will just allow these integrated circuit design to fabricate. Okay. So basically, the fab house style that the test must not be comprehensive, it must not be too long. So basically, they need to test the physical. They need to test physical hardware. So that they ask what type of test development you have did with your design in your design cycle phase. Okay. So fault coverage is a part that how many fault you have selected and how many, see, if you have a design, okay, in which there are 10 to 15 flip-flops are there, and some 20 to 25 universal gates are there, and some 2 3 inputs are there for input, and 1 to 3 output pins are there. This type of design you have. Okay. So basically, how many? First, you will select a fault model. Like you are selecting a fault model that is stuck at fault modeling. Okay. Like you are selecting a fault model. There are this number of circuit lines, total input and output intermediate lines, and every line can be stuck either on one, or it can be stuck on zero. So by taking this type of fault model, you have defined the circuit can operate for these different faults. On different faults, the circuit will then behave differently. So we will just generate some patterns and apply those patterns, and then see how much faults you are detecting with those patterns. Like if you are considering a fault at a time, it will result in different output. When you will see the absence of that fault, the output will be different. So when it is changing the output by applying fault on or disabling the fault, enabling or disabling the fault, that you can say of any input vector, the vector that we have result, the vector which is the result of test generation process is detecting the fault. So basically it is increasing the fault coverage. So basically if you have 100 faults, how many faults you have detected using your test generation, it is depend on fault coverage. Okay, so if you don't getting a good fault coverage, so you can just change you can grade your test generation process, that my test generation process was not enough good to generate large fault coverage. So then you will do some changes in your test generation process, and then generate the test again, and you can see the fault coverage and other things. You can check whether the fault coverage is increasing or not. Okay, so this type of things are the concern of design industries and vendors about the testing of electronic designs or integrated circuits. So basically, there is a question: what is the difference between verification versus testing? So, can anybody of you tell me this difference? Is there any idea about what is verification, what is testing? Can someone told me? Any student? So basically, verification is related to we have just created a design, like we have a function, and that function add two inputs. Okay, so we will check multiple cases on how many input it is doing this correct. It is doing correct addition. So basically, verification is related to the testing of functionality of design, like it is running on the like it is not deviating with it is not deviating on the functionalities if we are giving some different inputs. Like for some outliers, it is not changing its behavior. It is about the verification, and testing is about to analyze the defects of the design. If we will fabricate this design after manufacturing, or after we will fabricate the design, and after manufacturing we will need to perform a manufacturing test, and on that time what fault models we can apply, and what different type of defects we can minimize, and these type of process which is a subset of test development process related to testing. So basically, testing and verification are two different things. In verification, we just check the correctness of functionality. Okay, and in testing, we check the correctness of manufactured device. Okay, so you can see how diverse are these two things. So basically, also there have written verifies correctness of design, and testing verifies correctness of manufactured hardware. Verification performed by simulation, hardware emulation of formal methods, and testing we do using test generation and then test application. In test generation, we deduce the patterns to apply on the device, and in test application, we just apply them and compare them to the given golden response and decide whether the hardware is correct or not. So these are some differences in verification and testing. So basically, here we have justifying that why we need for testing. Like in recent decades, we have multiple incidents like Ariane 5 disaster is there, and other disasters are also there. Failure of any hardware circuitry can trouble you multiple times, can take you in very life threatening situations. In Ariane 5 disaster, if floating point multiplier give wrong output, and because of this only they will have a blast in that missile. Okay, So there are also multiple incidents with rockets and flights are also there. The failure of hardware inbuilt embedded on these on these things will get more troubles. So basically, this is demanding the good testing of electronics chips basically. So functionality is the issue is there. We need to verify the functionality where like we have to do the verification and density if we have a complex design, so we have multiple faults on locations, so density of faults will increase, so it will be the it will be difficult to generate that much test patterns. Test generation will be challenging for those type of things. Application issues are there, like in certain life threatening applications, we required maximum uh, correctness of design. So we have to gather a very good confidence matrix, and it will require a lot of cost. So basically, and for testing, the hardwares we use, the machines, 80 machines, maintenance cost for those 80 machines will be too much high. So basically, there is needing the attention. Matlab testing is gathering attention in recent decades because of these things only. So where there we have two types of test. We can see ideal test and real test. In ideal, basically in ideal test, we will just discuss all the defect in once, and then we will define the maximum number of combinations we can apply to this to solve this problem, and we can just apply those pattern and we generate complex simulations. We simulate all the process in ideal testing. But in real testing, what we do, we have kept some different objectives, and on the boundary of these objectives, we will move around. Okay, we have defined the state generation process, and we have defined this DFT architecture, and we have designed this evaluation matrices, and we have also determined we should receive this much amount of confidence you on the results of on the evaluations of test development process. Okay, so this is known as real test. So basically it depends on the design's complexity, how much complex it design, and so basically this ideal testing can take hundreds of years to select a chips with all this like all the possible simulation if we do, so it can took few of the years for some circuits depending upon complexity. So we do this real test. Basically we define the objective, we had defined the constraint, and we solve the optimization problem, and we do the real test in minimum times and considering the maximum fault coverage should receive. Okay, so we can see testing is a filter process. This is filtering how many chips are good and how many chips are bad. Okay, so this is a kind of binary filter. You can say a testing process of binary filter. That is classifying the given chips and good chips and bad chips. Is there any query till here? Guys, if you have some doubts, you can ask me anytime, okay? You can interrupt me in between and you can ask, and I can also go back to previous slides for clarification of your doubts.
Sir, like this ideal and real testing, the same thing applies to verification also. Like there is real verification and ideal verification, something like that.
No. It is related to testing. It is related to fault modeling only, okay?
Okay, so while verification, we do full exhaustive.
In verification, we see two or three topics are there, like verification through simulation. We can do simulation only. In simulation, we have two different type of simulation. One simulation is there. We can only apply a test bench using Verilog, and the other is we can apply system Verilog to test it. or UVM, universal verification methodology, we can apply. Okay, then the other is we can use other languages like E is there, VARA is there, and also we can use C language to do the functional verification. Also, functional verification is related to like we have a design, and the design is consuming like X watt power, and we want this design to consume less power than X watt. Okay, so that we do the verification, what are the certain points we will have because of these, we are just getting this much power. So this is related to, this is one more stream or one more thread of functional verification. Okay, but doing testing with some DFT architectures and test generation process uh, is divided into this ideal testing and real testing. Okay. So basically, I have told you that if we realize any integrated circuit, we turn some specification into a real hardware, and during this realization process, we come across multiple levels of design. Like we work on transistor level, we work on chip level, and we work on board level. So this level of testing indicate that whenever this we will just go in different level of abstractions of the design process, the cost of testing will be the 10 times of the previous cost when we go just on the next level. So like we have chip level. On chip level, we have certain components like here we can have transistors or here we can have gate level designs, and that will the testing of this chip will have X rupees. And if we just mount those components into a board and then we test whole of the board, then the cost will be the 10x. So it is better to do the all types of verification, and we can do wisely test development in this chip phase so that we do not need that much testing on board level, so that we can optimize the cost of testing. Are you getting my point? So when you increase the complexity, cost will be just too much huge, and it is increasing with the rate of with this rule of 10 changing on every level. It is just getting 10 times. Okay, so it is better to wisely test and fully test the chips on lower level of abstractions. Okay. So basically, what different levels you can see and you can refer to. These are here we have mentioned, like you can refer to transistor level, you can refer to gate levels, RTL level, functional level, behavioral level, architecture level, and different levels. You have some different kind of fault models, like in transistor level you can do the analysis of delays, that in how many time it is giving the response. And like in case of gate, you can just identify is there any gate is working correctly or not, whole gate is working correctly or not, like any pin of the gate is stuck somewhere. In RTL, you can uh, check for in RTL also you can check for multiple things. Basically, you you can do the testing of memory faults in RTL, or you can test some gate level faults also. You can test in RTL design. So you, in RTL design you can have multiple fault models. In functional also, behavior is there, architecture is there. In architecture you can also have memory faults. Okay, so you in next part of this unit 2 of this book or of this course, you will study about what are the different fault models we can have access for testing and verification purposes. Then it is all again indicating how much the cost of on what factors cost of testing is depending. So basically, I have told you DFT that basically DFT is a different architecture where that we are applying and or integrating with the existing design. Like you have a design which is implementing f function on your inputs. Okay, so you need when you will do the manufacturing test of that design, what you will do, you will apply some set of patterns, and for this purpose you will do the test generation. And DFT is related to applying the architecture like scan architecture, beast architecture, this type of architecture we are embedding with this f functionality. So it will increase the hardware area of the hardware, it will increase chip area overhead. And if uh, we are showing we are observing the increasing area, we can see there will be a loss in yield. Basically the testing methodology we are using, the AT machine we are using, the test development we are using will respond differently for change area. So basically it will finally reduce the yield of the DFT process. Okay, and yield is directly related to cost of testing. Okay, performance overhead, the time to market. I told that if you investing large amount of time with the test development, it is also making the process complex. Okay, so performance overhead will also increase time to market. It will take more time to deliver the final item to the customer. Okay, so cost of testing also depend on software process, like what type of fault simulation we are just replicating in test development process, and what are the test generation, different type of test generation we are doing, and how much test grading process we are, like how many iteration of these things we are doing. So it is related to software process of testing. Okay, if it then AT cost after implementing all the test development, we have gathered certain amount of confidence metrics on the design, and then we are going to deliver our GDS2 file to the fabrication vendor, and then they will, after fabricating, they will use AT machine, and the same test generation process, basically the same result of test generation process you have done in the test development phase will be applied to ATE machine with physical chips, and then we will see the real manufacturing test. Okay, so basically the cost of, here we have defined the cost of ATE machine and justifying the our statement how much this cost of testing is too much huge. So basically, if you go to for purchasing 80 which have 1024 pins, you will have to spend 1.2 million, or sorry, approx 4.27 million. If you run the running cost of the machine, if you have a machine and you are running machine, it will take almost 1.4 million per year if you operate it for 5 years, and the maintenance cost and operation cost are included in this running cost. Then when you applying the testing, when you apply the device and the result of test generation process and start a test application of real test application, then it will take 4.5 cents per second this machine is taking. So if a circuit is AT operation is of 24 hours, so it will take around 1.4. So this time, these testing processes are too much complex. Role of testing, I have already told you that we can analyze what different models, what different models are getting fail, and we can characterize the devices, that how much the design device is correct, and we can just define the this devices have can have maximum this much of errors, or we can diagnose the design with certain fault models. Okay, so these are the things, these are the component and basic fundamentals of testing we operate in industries. So this is a modern SoC. It will be have some processing core and it will be have some memory and other different type of logic. So basically, this is indicating that we have multiple come nowadays in SoCs. We have multiple components and we have multiple cores. So on board level, how much cost it will consume, how much it will be challenging to test this thing on SoC level, board level, and how much knowledge we require or how much technical know-how. Technical know-how means the all applications and algorithm you will require, all technical knowledge you will require to perform any kind of operation. So in this test application, how much expensive technical know-how is required to test all these components on chip level to reduce the cost. So this much complex is the process of doing testing and verification. So these things are in the introduction part, basic concept and definition. Then what are faults, what are defects that I have told you. If you have doubt in anything, what are faults, what are defects, and what are errors, or what is AT machine, these things, and what is DFT, all the terminologies I have told you. What kind of terminologies we will be used in this process. And the test economics and product quality also have told you that how yield is reducing if we have using some degraded test generation method. Okay, if we are using some bad test generation method, we have losing some product quality. So these things I have also told you. Fault models, I have also told you there are different fault models, and in detail you can study in chapter 4 of this book what are the different fault models. Then in test method, you will see what are the fault simulation, what type of different logic and fault simulations we can do, and what are the algorithms we used in fault simulation. They are basically concurrent, parallel, deductive, these type of fault simulation schemes, and they have different complexity and different type of functionality. Okay, so testability measures are there, like you can define how much complexity this design will take. You can just measure the testability. Basically, you can measure the complexity of testability by studying this chapter. And you will analyze combinational testing and sequential testing. How well, like what different ATPG you will require for combinational and for sequential. Also, you will see in the upcoming chapter that what test strategies you can use to memories and delay test and IDDQ test are there. Basically, they have different fault models. They are related to transition level fault. As I told you, there are different fault models. So these type of fault models, learning of these type of fault model will be the outcome of this second unit of this course. And there are also multiple software like in Synopsys for logic and fault simulation, and ATPG we have Tetramax, we have a tool, and in certain iterations we can do the test generation, and we can also select the methodologies they have deployed in the tool, and we can just see the patterns for this design. What are the patterns and how much will be the fault coverage? We can see practically these things on that tool, Tetramax tool. We can do the design synthesis process and gate level design synthesis and basically DFT process on Synopsys Design Vision tool. Here there are certain steps or certain iteration. You can define your DFT architecture, your DFT second, and you can simultaneously do the DFT on the design, and then you can evaluate the response of test generation. It will provide you the pattern, or also it will provide you the test bench or just a simulation file. It will provide you, and you can simulate that file, and you can calculate the matrices also using VCS and worthy tools. So there are different tool chain are there provided by different companies. Synopsys provide different tool chain. Cadence have provided different tool chains for performing all these things. Okay. So then in third unit, we will specifically have all these DFT topics like scan design, what is scan design, what is based, what is boundary scan. These type of things are will be covered in DFT or third part of this course. How you can design these things and how can you can evaluate the performance of these DFT techniques and what will be the testing strategy for this type of testing and what will be the ATPG techniques will be appropriate with different type of this DFT schemes. These things will be covered in DFT session. So I think it's all about the introductory session. And if you have any doubt, you can ask me. Uh, is there any doubt? I have concluded today's lecture. And in last, I can, if you want me to summarize all the things, I can summarize all the things one by one.
Sir, is this class will continue from the next session from tomorrow also?
We will tell you first. This session is over, no?
Session is over. If they have query and they want me, or you want me to summarize all the things I have told, so I can just do these things in math.
What is their query? Yeah, what is your query?
My query.
No, their query.
Okay.
If it is there related to the subject, you can tell them. Otherwise, if they have something else, they can contact me personally. I will tell them.
And one more thing I want to ask. I want my feedback that how much.
Yeah, within 3 days we
knowledge-
will give the feedback. Don't worry. Yeah.
and
Okay,
I,
fine.
okay.
Okay, fine. Thank you guys. Thank you so much.